And today I want to talk about diffusion generative models, as we just saw in the previous talk, and some applications for collider physics. Let me just turn off the sound from my own computer, otherwise it keeps getting feedback, sorry. And I'm really glad about the workshop so far, since we not only we have an introduction to diffusion models, but also symmetries we saw in the morning that is also going to be very important, and some other topics that I can go quickly through my presentation. And today I want to talk about 3 different applications that I've been particularly working on. They're not the scope of all applications in collider physics, but they kind of give you a flavor of what's going on. Even though diffusion models are somewhat recent, we've already been adopted diffusion models for a number of different tasks. So starting with fast detector simulation, I wanted to have one flashy slide just to talk a little bit about particle physics in general, since the audience is very broad. And the goal of particle physics, or in the case for collider physics that I want to focus on, is to do collider experiments. We smash things together and try to understand the universe out of that. And in order to do so, we use often LHC observations coming from the LHC experiments in Switzerland. And we also had a great introduction to particle physics in general from Javier's talk a few days ago. And the idea is that we have these very big colliders and these very complex and very precise experiments that can do measurements of these particle collisions in order to give you insights about how particles interact and what are their properties. And using these insights, we can go to the theories that we currently have that describe these interactions, the standard model of particle physics, and see how well these theories can model what we actually observe in experiments, and maybe even going further, going to look for new physics that are beyond this standard model of particle physics. But one major aspect of this comparison between theory and experiments is that we need to translate our theory predictions into something that we can actually compare with our experimental observations. Which means that not only do we need to put all the physics knowledge that we know about particle interactions and what happens between these particle collisions, but we also need to have very precise modeling of the detector response that we are currently using within the experiments to actually do your real measurements. Which means that we need to simulate all the different components of your detector. In the same way, we need to have a precise description on how different particles, they are the ones that we want to study, they interact with the detector material. But something that is pretty tricky to do is the simulation of calorimeters, which you cannot see from the screen, but from the pointer. But those are within these blue boxes, which corresponds to the part of the detectors that basically stop the particles going through, making them interact with the material, depositing energy within this material, from where we can then infer what kind of particle was passing through. Was it an electron? Was it a pion or some other type of different particle? And also give us the information of the energy of this incoming particle going through. But this guy is very computationally heavy when you want to do a full simulation, because your detector not only is very granular, you have this shower pattern. So the more energetic the particle is, the more it interacts with your detector, the more it creates these showers of detector readouts that you need to simulate. And not only is this a problem conceptually, but it's also a problem that we foresee in the future that is going to be a major bottleneck unless we do something about it. Because, for example, if you look at these plots on the right, on the amount of CPU hours versus the years, so far in this line, we can see in the amount of budget that we have available, the computing power that we have that was majorly used for simulations was perfectly fine. Our simulations could be able to be run very nicely. But if you see in 2026, when you start to ramp up the amounts of instantaneous particle collisions that we have at the LHC, where you're going to gather a lot more data in a shorter period of time, this budget suddenly increases exponentially, and the amounts of computing power that we need increases exponentially. Meaning that unless we have an exponential increase in the amount of budget in your experiments, which is not very feasible, we need to define some different ways in order to bypass this issue, or trying to identify ways that we can speed up parts of our simulation to be able to cope with what we actually have in order to keep up. And that is one of the main motivations of trying to use surrogate models or generative models that in principle can do this task for us. So imagine that I can train a generative model to simulate the response of an electron of a certain energy going through my detector in a way that is not only very precise and reproduces what your detector would actually tell you about these interactions, but it's also very fast in a way that not only can use GPUs, but even a single CPU, you hope that this would also be faster than doing a full simulation of your process. And hopefully you want the best of both worlds, right? We want something that is very accurate, but it's also very fast. There are some other options for fast simulation using machine learning and also not using machine learning, which often makes some simplified assumptions about these interactions, which makes the simulation very fast, but not so accurate. So maybe you can do something better. In this idea, we're trying to push some generative models within big experimental collaborations with thousands of people working together, which would normally seem like a nightmare for most of people. It's actually something that is happening within the Atlas collaboration, for example. They already replaced a part of the calorimeter simulation that used to be a more complicated simulation routine with a Wasserstein GAN, a generative model that does exactly that. That tries to simulate the response of a particle going through your detector and to detect the energy deposits of this particle. So for example, if you look at this histogram on the right, if I have an electron with this fixed energy and I keep shooting these electrons and I want to know what is the deposited energy that these electrons are leaving my detector, you get the histogram in black for the full simulation and in red for this Wasserstein GAN. So you can already see that it's pretty nice. It does reproduce what you want to see. And if you look at the architecture that they are using for the Wasserstein GAN, something that is very simple. It's a bunch of fully connected layers that can run extremely fast, thousands of times faster than the full simulation. But one of the simplifications that they do is that instead of trying to emulate the full detector geometry with all its final components, you almost flatten everything up beforehand and you voxelize it, which means that you combine some of these detector readouts together in order to minimize the amount of empty detector components when you're doing your simulation. So maybe you can try to do something that is slightly better in the sense that we can try to incorporate even more information about your detector geometry and how your detector is responding to these particles by using some other methods that may be able to also give us some nice results. On the left, that would be my very quick introduction to diffusion models, but Carsten did a much better job than I could do, so I won't talk about that. But the main point is that either directly or indirectly, for every diffusion result that I'm going to show in this presentation, the goal is to learn this score function, the gradient of the log probability. And to show that this approach can actually work for detector simulation, I will show some results on this recent simulation challenge, the fast calorimeter simulation challenge, where the goal was to propose different models that could try to reproduce one of these three available data sets. We had one data set with 368 voxels or detector readouts they want to simulate. Everything was flattened out. The information of the detector is not very complete in this case, but the other ones are box-like detectors, where we have 45 layers. Each layer is a 12 by 12. That's data set 2, about 6,000 dimensions. The other one's much bigger, more granular, 45 layers, 32 by 32, giving a total of 45,000 layers, 45,000 components. So that's the goal that we want to simulate. So for the model that I'm going to use to simulate these big data sets, they're going to be basically UNets, using either three-dimensional convolutions for these data sets that are like a box with three components, or a one-dimensional convolution where even though the data set has been flattened out, the correspondence between pixel readouts that are close to each other still give you some information about the location in space. And now everything's black. Oops. Did something happen? No, okay. Well, everything turned black before I show the results. Where here, what I'm showing is, for example, for data sets 2 and 3, what is the average energy that I record with my detector versus the layer that I'm looking at, which means that in the beginning, in the first layers, the particle is starting to go through your detector, does not deposit a lot of energy, starts to deposit more and more until you reach maximum, where now there's not much energy left. So this particle has to deposit less and less. And here is interesting that if you look in green, you see the response of what we get from the diffusion model. In pink, what you get from a Wasserstein gun. With architecture, it is almost the same as the UNet that I was showing before. It's just that you decouple the left and the hand side parts for the generative part and for the discriminator. And here you can see that the Wasserstein gun fluctuates a lot compared to the diffusion model, which gives you a nicer response. And if you were to take, for example, the average response of 10,000 showers in a specific layer, that's all you get in these plots on the right, on the top for the full simulation, and on the bottom what you're generating using a diffusion model, which is really nice because at least visually they are pretty similar to each other and they have the features that you expect. You're shooting a particle through the center of your detector. Most of the energy is at this pixel at the center and then spreads out a little bit further away. But the other thing that is important is look at the time, because we also saw from Carsten's talk that these models, they are not very fast, because when you're sampling, you need to use either some stochastic sampler or some OD solver, where no matter the choice that you're taking, often leads to hundreds of function evaluations, which means that for the UNAT model that I'm showing, I had to evaluate that 100 times, for example. But even having to evaluate that model 100 times, the time that it takes to generate observations compared to the full simulation is still more than an order of magnitude quicker, which is also pretty nice. So you can see the comparison for the color score, which is the diffusion model, and in the last column, the full simulation. But having things that are a bit slower and okay are nice. That's a good proof of concept. But we wanted to do one step forward and trying to iterate from this work that we did 1 year ago. So now we have a version that's called Color Score B2, which is not very creative, but bear with me. Where the idea is that, well, two of the shortcomings that we observed, one was the time that it takes to generate some new samples that I'm going to talk about later. But the other one was these energy depositions in your detector. So the amounts of energy that the particle deposits in a detector is very important, because not only that gives you the information about the incoming particle that you want to have more information about, but it's also used for a number of things inside the collaboration. You need to calibrate these quantities, you need to have something that is very precise. But compared to image problems, the sum of the pixels does not give you anything. So that's nothing that is often enforced within normal diffusion models. So what if we try to do two diffusion models? So one that is only focusing on trying to get correctly the amounts of energies that have been deposited in the detectors. So this guy can be just a list, in this case of 45 features, if I have 45 layers in my detector, that I'm going to run a separate diffusion model on. But then I have another one that is conditioned on this first diffusion output that tries to generate the detector readouts that have been normalized by the layer energy. And that's what you're going to see here. We're not only using the separate diffusion model, the energy response that you get is a lot better compared to what we had before, which can also be evaluated using the Wasserstein metric for these one-dimensional objects, where for each of the data sets, you see a big improvement. Lower is better in this case. But also improves the overall generation of these diffusion models, because basically now that you're normalizing the energy deposits in each layer, means that in the layers where you had very low energy deposits, but you wanted to still be very precise, they're now treating equal footing compared to the layers where you had a lot of energy beforehand, just because everything now is normalized. Another change in the overall architecture in this follow-up work was to introduce some attention mechanisms to the UNet to make it a little bit more expressive. So in the lower dimensional spaces, we have some transformers that I apply there to create the patches and get your attention coefficients from this, which also improves not only the model fidelity that we get at the end, but also make the model faster, just because beforehand, in order to have this more simplified UNet, the size of the convolutional kernels that we are using were extremely huge in order to be able to get some fine information within these very sparse data sets. But the transformer can get that a bit easier without having to do so. And the other major change to the model is that I mentioned that we needed to use 100 steps in order to generate something that looks like our simulations, which is fine, but not very fast. But what if we try to do something extra? What if we try to train a distillation model? So we try to use this idea of progressive distillation, where the idea is that, well, you train your normal diffusion model as you normally do. That requires how many time steps you start with, let's say 4. After you train this diffusion model, you can train a second model, that is a student model, that learns with the teacher, that is this initial diffusion model. Where the idea of the second diffusion model, or the second model, is to learn how to interpolate 2 steps of the solver for the initial diffusion model. Where at the end of the day, what you get is that a model that can generate with the same fidelity what you want to simulate, by using half the number of the total time steps that you require for your initial diffusion model. But you don't need to stop there. You can keep going and changing who's the teacher and who's the students until you go to a single step where you basically start from the noise distribution, do 1 step, and you get directly your simulation. And then you are at the same level of complexity, quote unquote, with a GAN or other models that only require 1 passing of your network. And doing that gets you some very nice timing improvements. You get orders of magnitude compared to the full simulation, more than 100,000 times faster, and also much faster than the previous CalScore model that we're showing. Then the question is, well, with this 1 step, can I still do things that are nice and look like the simulation that I had before? And the answer is that for the model that I was showing in the previous slides, I was already showing the single step without telling you. And here I can also show you, for example, how does the average energy depositions in different layers of my detector are simulated either using the single shot generation on the right and on the left for the full physics simulation. And again, visually, you see that they have the same properties and everything is also pretty nice. So even with a single time step, single function evaluation, we can generate from the trained diffusion model something that is still very high fidelity, not only better than the model we had before, but also better than many different models that use different methods. And before I keep going on for the next topic, do you have any questions so far?
Yes, this is something. Yeah. Yeah, these results look really, really nice. I was wondering for the single shot. So if I understood correctly, it means it requires training the original diffusion model and then several steps of training student models on top of that. I was wondering, since the final thing is this single shot, is it, do you think there might be a way of speeding up that training paradigm in the sense that like maybe there is a way to go directly to that without kind of all those intermediate steps? Just curious.
No, yeah, that's a great question. And indeed, there are some other methods for distillation that don't do this progressive training, where they basically start from some trained diffusion model and can do a 1-step distillation that can reduce that, so go 1 step directly. That is, of course, possible. From the training itself, I don't know of any model that can do single shot from training just once a diffusion model, not that I'm aware of. And we are going to look into the future of these different alternatives for distillation. But in this case, for the progressive, one of the advantages that we observed is that we could, for each of these subsequent neural networks that we're training, we could be very precise, or the error for our predictions in these 2 time steps could be very small. Whereas in the case that we try to do this single shot step, now try to interpolate everything all at once is a lot harder. But I'm not saying that it's impossible because I haven't tried it. But at least for this progressive distillation, that's more of the intuition why you go into these subsequent steps. Any other questions? Yep.
Just a question regarding the theory behind progressive distillation. Is there any sort of theoretical guarantee that on the fidelity as you sort of coarse grain in time, or is it something you're just observing empirically?
Yeah, because basically what you do in the progressive distillation is that you can solve the overall diffusion model without distillation as solving an ODE problem. And you can discretize the ODE basically in a number of different time steps. And all you do in the progressive distillation is that you do 2 time steps from the ODE solver, and you try to match with your network, the output of these 2 time steps. There's no guarantee in the sense that how well your neural network can approximate these 2 time steps, but if you can approximate perfectly, then you reduce guarantee the number of time steps with 0 error, basically.
Thanks.
If there are no other questions, let me go to the second topic, what is jet generation? Because before I was talking about simulating the detector responses and parts of your detector that measure the energy of your particles. Something that could also be very interesting and could also speed up simulation or could be used in different parts of your experimental tool set would be to try to generate particles directly. Or for example, you have your detector readouts that can combine the energy deposits, the tracking information of your particle as one reconstructed object, and those are the objects that you can try to simulate. And one of the objects that are very important in high-energy physics that we also saw from Javier's talk is to try to simulate jets, so these collimated sprays of particles that are created from color particles, where the idea is that you have particle that has been created through the particle collision on the right, and this particle starts to emit, fragment, and create these collimated jets, where you have this sort of cone-like shape, where you have lots of particles inside, seeming from almost the same primary vertex. But now we have some additional difficulties if you try to generate this kind of data set, because now it's not an image. It's more akin to a point cloud, because the properties that we want to be sure that we can reproduce is that one, the particles that I'm generating, they need to be permutation invariant, or in a sense that I don't want my model to be figuring out the different permutations that I can have for the different particles I'm trying to generate. And the other property that I want to have is that I don't want to have a fixed number of particles that are going to be generated, because then amount of particles that are clustered within a jet is not a fixed number. It's also an important number, because that can give you information about the different particles that created the jet beforehand. And the data sets that I'm going to show for this study, they come from the JetNet data set, which is a public available data set containing different types of jets, which means that I have different types of these objects that I want to simulate, created by different particles, where each of them also leaves you with different signatures. For example, if I want to simulate the response of a light quark, what my expectation is that I'll have fewer particles inside of these jets, and they'll be very close to the center of this cone. But if I have something that looks like a top quark that has a 3-body decay structure, then I expect to see almost like 3 smaller cones within this bigger cone. So they can be very different from each other. The number of particles they expect can be very different from each other. And in these data sets, you either have 30 particles in total, so you truncate, or you have 150. So you also need to deal with this far-right number of particles. So what kind of architecture we can use within the diffusion model that can do this problem for us? Because from the diffusion model structure on the training, you don't need to change anything. It's more about trying to incorporate the properties that you want to have within your models in their model architecture that you're going to use. So for example, I want to generate separately the number of particles, because then a model that can generate particles conditioned on this number can generate correctly the number of particles that I want for each individual jet that I need to generate, together with some other jet kinematic properties, like the overall mass of these jets, or the overall momentum of these jets, or the positional space where these jets hit my detector. Then I can have a second model that is conditioned on this first guy that only tries to generate particles relative to the overall position of the jets that I generated the first model. Where the second guy, now I need to put some permutation invariance. In this case, I need permutation with covariance. I need something that if I just permutate my inputs, the score function will also permutate the outputs. And something that is very easy to accomplish within machine learning is use a deep sets model, or something that does not look at the individual particles, but just apply a function to all of the particles, the same function to all of them. Of course, just applying that can give you some power to distinguish between the different particles that I want to generate, but it would be nicer if you have some additional mechanism that can be used in order to get the correlations between particles in a nicer way. So for instance, we can use a transformer blocks in between, which also have the same properties that we want to have within the particles that we want to simulate, and can also enhance the model capability in order to get something that has a higher fidelity. And the nice thing is that not only we can generate jets with the properties that we want, but also we can do the same progressive distillation that I was showing before and get something at the end of the day that has very close to the same fidelity as what you'd have from your initial simulation. So if I want to look at the average response of a top quark jet, that is this guy on the left for the simulation, where we had this kind of three-body structure where one is in the center and the other one is a bit fuzzy, combining this y-axis, where all the images were first aligned. You see that training the base diffusion model, you get something that not only is very close to what you want to simulate, but also after you do these steps of the progressive distillation to reduce the amount of time you need to generate, you also obtain something that retains all these nice properties. And I don't need to just hand wave and say that is good. I can also show some a big table that you can look later, comparing different metrics that are inspired by some physics, quantities that we want to have a very precise modeling within these generative models. And compare that not only for these models I'm showing for the diffusion, that are the three ones on the top, but also for some other models that have been proposed in the literature. And if you look at the bold quantities representing the best for a particular metric, you see that the diffusion model most of the time is doing a good job. And also, even when you do the distillation process, you still retain a lot of this capability. And just a bonus before I go to the last topic is that I was showing how to generate detector readouts using a diffusion model that is based on images, basically, because I had this big box and I simulate the big box. But then I show you a nice model that now uses a point cloud description of your data sets, where you just have the particles and their properties, and you want to simulate that instead. So what is better? Can I try to use this model as well for the simulation of detector readouts? Because one of the problems that we have when you're trying to simulate the full colorimeter response is that often if you just look at a single particle going through, I want to simulate a single electron, then the amount of energy that is deposited in a single layer is taken here on the plots on the right, where you have this single pixel over there, but everything else is empty, which is by design made to be like that, just because you want your detectors to be very granular, very precise, and to not have overlapping responses for different particles that might be going through the same detector direction at the same time. But that also means that I'm trying to simulate an image that is almost empty everywhere, and only a few spots that have something that is not empty. But instead, if you try to do this point cloud treatment where you're not trying to simulate everything, but just trying to simulate the detector hits, then you have the advantages both on the computational side, because now your data set is a lot smaller. It does not need to take into account the full detector readout with thousands or even millions of detector components, just the number of hits that can be hundreds to less than 1,000 in this case. But also just is more memory efficient and don't need to save a bigger data set with millions of entries that are basically empty. And this idea still works. You can do here in the bottom for a different detector where now the particles are not going through the center, but they have an angle. And you're generating for different layer numbers again. On the left, the response from the full simulation, and on the middle, what you generate, but now using a point cloud treatment of your detector setup. Which again, just looking at these images, they look nice and very comparable to each other to this visually. So before I go to the last topic, do you have any questions?
Thank you. If you could go back to the slide where you had the top quark generation. So in the full simulation, you kind of have this like separation of the two blobs, which is kind of captured when you do the full diffusion model. But then when you go to the one step, that kind of separation is like removed. I guess my main question is, do you have a tolerance for how much the fast simulation can be wrong? And does the one step kind of fall within that tolerance for this particular problem?
Yeah, that's a great question, because indeed, it's not like the progressive distillation is lossless at the end. You have some small loss in performance for each of these steps that you apply in the distillation procedure. And indeed, you get some more fuzzy images at the end, or more fuzzy particles, which means that indeed the blobs, they kind of overlap. We can also quantify this sort of performance using different metrics that can tell us or guide us to what is the level of distillation that I'm willing to apply in order to get some level of fidelity compared to, for example, other fast surrogate models that is also fast enough in order to be able to be usable within an experimental collaboration. So in the case of 8 time steps, where you require 8 function evaluations, that is a little bit better. You can also see from the metrics that 8 time steps is often always better than 1 time step. But even the 1 time step, for a number of these metrics, they can still be very competitive with other models that do not use diffusion at all. So it's a trade-off between performance and speed.
Can I ask about the particle number conditioning? So
yes.
I understand the technical reason why we need to do that, but do the models at different end, do they know, do they have any information sharing, any weight sharing, or are they completely independent networks?
No, they are not completely independent. They are all conditioned on the number of particles that I want to generate in a particular jet. So at the generation time, but during training, they are just conditioned on n, and my inputs have n particles. When I want to generate, I first generate what is the number of particles that I want to generate, give the number to my model that has been conditioned to that, but I also force my model to output this number of particles. So it's like not having different neural networks for this, but since it is conditioned on the number of particles, each neural network already knows what it's trying to simulate.
And it's conditioned just with n input as just a number n.
Exactly.
Thanks.
Any other questions?
Yeah, so let me go to the last topic. It is on density estimation and anomaly detection, which doesn't sound like anything that I've been talking about, but it's also something that is very interesting, because I was alluding to in the beginning of the talk that we study the standard model very precisely, because one of the reasons that I want to understand nature, and another thing that would be very exciting, is to find something that we haven't seen before. And we have good reasons to believe that there are things like that, like the extent of dark matter that we don't have a good explanation for. And trying to find a model that describes how dark matter works is not that hard. The hard part is to take that model and apply to your experimental searches and find them all. Because the moment that you set the properties of the model you're looking for, you can be very precise at trying to identify this model within your data. But if you don't know what you're looking for, then you're in for a challenge. And that's the idea of anomaly detection. So I want to find anomalies within my data sets, which means that I want to find things that are not looking like the standard model of particle physics. And the thing is that if you hear the term anomaly detection, and if you work on anomaly detection yourself, you might be more familiar with trying to look for outliers that are very far away from your data set. Meaning that with just a single example, so if I say that the picture on the left represents the garden of the house that I just bought, then you'd be very, you'd not believe me just because, well, the picture is weird and I'm a postdoc, I cannot afford a house to begin with. But you can see that in the case of particle colliders, things become a lot more blurry, because from a single particle collision, you cannot just identify by looking at it if it corresponds to some new physics, something extremely exciting, or if it corresponds to your standard model of interactions. You need some way to quantify how things look anomalous and use some criteria in order to identify your anomalies. So for example, in the right, when you're looking for the Higgs boson, the moment that we didn't know it existed, then the Higgs boson itself was an anomaly, even though right now it's a well-known particle in this full standard model. So that would be a very interesting way to do that. If you could, for example, try to estimate what is the probability density for a jet containing particles inside. Because then if I can train this method that estimates the likelihood of a jet within a data set that I know that is composed at least majority for things that I understand, then for the things that I don't understand, the likelihood of this observation will be very low. And that is the idea of the method I'm going to show here, where the heart of this method is probability density estimation. Of course, using probability density estimation can be a bit tricky just because calling something rare is not an intrinsic property of your particle collisions. It depends on the set of features that you choose in order to identify what describes your observations. But at least for a fixed set of kinematic properties that you want to use, you can then identify what is rare within this scope. So the idea would be, well, let me look for things that are rare compared to the majority of the examples that I have there. But now I need to have a density estimator that is that corresponds to all the nice properties that I have for my jets. That, for example, the probability of a jet should not depend on the permutation of the particles inside the jet. And if you're trying to do that using, for example, a normalizing flow, that is possible to do, but very tricky in order to be able to put these symmetries within the model, just because of the Jacobian restrictions that you often have over there. But from diffusion models, you can use the probability flow equation. That is something that Carson also mentioned in his talk, where if you go from the stochastic differential equation to the ordinary differential equation, the guy that takes the stochastic part out, you can define the log probability of your data based on the log probability of your Gaussian prior, given plus this integral here that you need to do that takes this function, the divergence of this function that comes from the equation on the top that uses this core function that you just learned with your diffusion model. So basically, the moment that I train the diffusion model to generate my jets, I can go backwards and get the probability density of these jets just solving an equation. And before I move on, to show that it is probability invariant, I can show you these plots on the right, where for a single jet that I have a number of different particles inside, for these three kinds of jets, QCD, that is showing orange, and that I also use for the training, or a Z prime, so something more exotic that we don't know about, or even a top quark, which is not so exotic, but is very different from what I use for the training. And I take different permutations of my inputs. The probability density that I'm getting, which in this case, negative log likelihood, is the same, no matter this permutation I'm taking the x-axis. And then we can define, for example, an anomaly score that tries to identify what is anomalous within your data set. And if this anomaly score is the minus log p divided by the number of particles that I have in my jets, then this guy will give lower numbers for things that are common within your data set. So if I train it, for example, using just QCD jets, then QCD observations will be more likely, meaning lower score, compared to everything else that I can compare, like the top quarks and the new physics scenario. But then I can train a different sample. I can train a sample using top quarks instead. And now top quarks are lower and everything else is higher. And we can use this score, for example, to identify things that are away or less likely within the data sets that we use it for the training. And things became black again. And if you look at the ROC curve, so now I use this anomaly score, train it, for example, on QCD jets, and I want to see how well I can reject other types of jets. Then you can see here for both the new physics scenario of these long-lived particles or some top quarks, and you can see that even for a good true positive rate, let's say 80%, so I can retain 80% of my anomalies, to a 10% retain ability of my standard objects that I have in my data set, which can be used then for anomaly detection, or at least a variable that can tell you things that are anomalous within your data set. So that brings me to my conclusion, and I'm out of time, so I will stop here, and let me know if you have questions.
You have time for a few questions. I just have an overall sort of motivating question. I've heard about Caligan and various GAN techniques and generative models to simulate GEONT and things like this over time. diffusion models are sort of the new kid on the block in this world, and I appreciate that they're slower. Is there any sense ahead of time, maybe just empirical, that it was clearly going to be competitive with these other techniques, or was it just something that you guys decided to look into, or?
Yeah, that was one of the things that we wanted to look to, just because, well, in the literature outside high-energy physics, diffusion models were very competitive already against GANs, which is even more exciting because GANs outside high-energy physics, they have been optimized to death for 10 years or so. And even then, diffusion models in 1 or 2 years could already be or competitive or even better. But the other thing is that whenever you talk to someone that trained it again, you see the frustration in their eyes because it's very hard to optimize a gun in a way that you're always happy about what you get in the end. So most people, what they do is to train a gun, they find one metric that they will be happy about if the metric is well simulated. So that's the condition to stop the training. And use this single condition often as the criteria to define what is the best model that you'd stop. But in the case for the diffusion model, you're just approximating the score function, thinking the model with the lowest test loss function, loss quantity is a perfectly fine way of defining what is the more optimal model in this case that do a good job at the end.
Yeah, and I appreciate the point. And because they were already competitive purely in image generation, you thought it might work here, and you knew ahead of time it might have run into timing problems, and this progressive distillation just solves the problem.
But even compared to GANs, for both the jet generation and for the detector simulation, we see some advantages already, even without the progressive distillation.
Any other questions for Vinny?
So I have a question just about kind of the reaction of the community to you know, just the general idea of generative models this way. So of course you need a training data set.
Yes.
We spent a huge amount of computational cost already on generating training or generating these training sets to begin with. Of course, if you don't have that kind of ground truth information, like in the case of the JetNet example, like you're trying to match something that has already been created. And you know, I think there's a question of how you're going to use it. Of course, having a model allows you to do things that you can't just do if you only have samples. But can you just kind of talk about the reaction, maybe more inside of the experiment, to like how these things are being used? In the case of detector simulation, like that, I think seems very straightforward as an application. But the kind of particle generation case where you still need theory to tell you what the underlying target is. Yes. And you're kind of trying to mimic that. What is the reaction from the experimental community, or thoughts about how one would do that? And I should say, as someone who's in that table, and I'm basically asking you the same question that I'm asked about, like, why are we doing this at all?
Yeah, that's a great point. And indeed, full simulation is always going to be necessary. That's why there's also additional efforts of people trying to just accelerate the full simulation, either using new hardware or just making faster in general. But in the moment that you need to generate billions of simulations and billions of simulated events, having a generative model can give you this edge just in the high scaling computational things that we need to do. The interesting thing is that there has also been some studies that even if you train with a smaller sample, let's say 1 million observations, and you want to scale that to 10 million, 100 million, the generalization power of the networks they're getting, at least in their case, was for a GAN. So that does not mean they translate to every model, but just the generalization power that you could gain from these models that were trained on fixed number of targets could extrapolate to higher numbers. So you don't need to have the same number of observations to train a model in order to get the same level of precision for this model when you're trying to scale up for the full generation procedure. Also because there are some symmetries and other things that can constrain the problem even further. So that's the insight. For the particle generation, or the jet generation in this case, I don't remember seeing that being used directly already within experimental collaborations. But often what you need to do is that, for example, I want to estimate what is the QCD background for my analysis that has a very specific kinematic cut. So I know what is the dijet mass that I want to look at, or I have a jet PT restriction coming from a trigger. So I want to look at jets at this particular region of the phase space. In this case, of course, you can take your full simulations. Your QCD simulations can be okay, sometimes can be not as good. But the point is that if you're looking at details or somewhere where your simulation needs to struggle to generate this kinematic phase space, that can be pretty tricky. But if you condition your model, in this case that I'm showing with the kinematics of the jet that you want, then you can directly just generate the samples within the region that you want to study. And you can either use that for a real analysis and use that as your background prediction, but it can also be used for feasibility studies, just to know what is the shape of your distributions and how well you would be sensitive on your search based on the background description.
All right. Let's thank Vinny one more time.